All right, so chapter 9, gravity, and looking at our introduction here for chapter 9. And, oh, actually, the introduction is here. I just want to say something real fast about the introduction, just because, again, it's, I don't know how it's an introduction to gravity, but let me say this, that Kepler in I think the early 1600s. He's the one that eventually figured out, doing a lot of math and looking at observations, that objects in orbit had to follow an ellipse with the center of mass at one of the focus points. So an ellipse has two focus points. A circle is when when these focus points comes together, and that's when you have a circle. Then circle is one focus point, you could say. And the center of mass is based upon the whole weight of the solar system. But for simplicity, we'll just say the sun is our center of mass, even though the center of mass is a little bit off center from the sun. But objects orbit in an ellipse. And this was Kepler's contribution that he figured out. And then when Newton wasn't alone, even though we give Newton a lot of credit for things these days, and I personally do think Newton is the king of geniuses in physics, but he wasn't alone in coming up with gravity. He also worked with Hooke. Hooke, who we give credit to for the spring, we call it Hooke's Law. He also worked with Halley. Halley, you may know the name for Halley's Comet. They all worked together in coming up with the result for the force of gravity. And what they worked on was the math. They looked at, well, what math, what force would I have to have that results in this type of motion? And then when they looked at that, that's when they got this idea that, well, it had to be proportional to what we call the inverse square law. The inverse square simply means that your variable is in the denominator, because that's what inverse means. So here's 2. If I take the inverse of that, that's a half. Inverse just means switching numerator denominator. So inverse is in the denominator here, and it's squared. So we call that the inverse square law. And that's what they figured out looking at the math, that this force must have to be. And they also included the masses here, like mass 1 of your object, mass 2, because in order to feel gravitational force, you have to have 2 objects, divided by r squared. And ultimately, there's this big capital G, that is the gravitational constant. One of the constants of we call a physical constant. So like pi in math, G is special in the universe. It's this constant that we believe is throughout the entire universe, G. And that had to be measured experimentally, the value for G. With the Cavendish experiment was the first one. I did this experiment at ASU. Very tough to do because the force of gravity is so weak that it's very hard in a laboratory setting, which is much smaller than the Earth, very hard in a laboratory setting to actually measure this value. I think my group and we got within maybe 15% or something, and we were supposed to be happy with that, so we were. But yeah, very tough to measure. A G has to be done experimentally, and it's just because it's so difficult to measure the gravitational force in small areas. Because the gravitational force is incredibly weak compared to the other forces. For instance, the Earth is massive, and it pulls us down to the ground. The gravitational force feels very strong because you jump up and it immediately pulls you back down. But what is actually supporting you? Why don't you fall through the Earth? If the Earth's gravitational field is so strong, why doesn't it just pull you right through the dirt? Well, and that's because the electric forces, things that give us like electricity, the electric forces are what are responsible for holding us up. So all matter, well, I can't say all matter. Most normal matter, I guess maybe I should say, is surrounded by electrons. And so when 2 things come in contact, these electrons repel each other, trying to push away. And it's this electric force, this repulsion between the electrons that actually holds us up, and that fights off the entire gravitational field. So we don't get sucked through the dirt. because all these electric forces are holding matter together and can easily counter the force from gravity. So gravitational force, very, very weak compared to the other fundamental forces. The other fundamental forces being electricity, magnetism, the weak force, which gives us decay of particles, and the strong nuclear force, which holds the nuclei of atoms together. So that's the weakest one, G. And that's kind of a quick history of it. Came about originally experimentally because they found this data experimentally. Then when the universe exhibits patterns that we can match with math. So one of the things I think is interesting about physics is that the universe does have patterns to it. And those patterns are math equations and functions. And so that's what they found in the ellipse. And then a couple people worked on what math would have to give us, what force, I can't say it all weird, what force using math would have to give us this elliptical motion. And that's how they ended up coming across the inverse squared law there. This is the official force of gravity that is from Newton. We'll call this Newton's gravitational force, because there's also Einstein's. And we'll get into that a little bit with gravity here because I noticed it's towards the end. But for now, it's just my quick introduction, a little history there, how that came about. And check out what they first have to say, the universal law of gravitation. Now, this apple story with Newton is, I know, something that's highly debated on whether that actually happened or not. It may have been just an idea he had, like, he was sitting in his office thinking of an apple falling versus actually being watching this happen. So kind of a myth, I think. He probably just thought about that sitting in his office or something, or maybe on a park bench, who knows. The point being, I don't think we really know anymore. But the Newton story with the apple, interesting, but may not be true. And here they're talking about, there's our force for gravity right here from the mouse. And I guess that's what they're motioning for. I noticed some arrows here with stuff. And this is one of the things that can be a little bit confusing with gravity, is it's commonly said that your gravity is, you're always falling towards Earth. And I think there's two scenarios that get mixed up that aren't always clearly explained. That if I am just falling towards the Earth like this, well, I'll eventually collide with the Earth. I'm falling towards the Earth, and I will impact the Earth. However, that's not how satellites behave. It's not like we have a satellite in orbit, a satellite, and it just falls straight down, because a satellite is moving. It has an orbit, which means it has some velocity going around the Earth. And so there's these scenarios. You can fall to Earth with no velocity left or right. If there's no velocity left or right, you're going to fall and hit the Earth. However, if you have a proper enough velocity, which we can figure out, then as you fall to Earth, you'll keep orbiting around it. But in order to do this, you have to have a very specific velocity. And again, we can calculate that from physics. It's beyond our chapter here, but if you have a slower velocity, then you'll fall into a spiral pattern and you'll eventually hit the Earth. If you have a faster velocity, then you'll start to spiral away. So you have to have a very specific velocity so that as you're always falling to Earth, you're always moving to the right. And that may sound a little weird, but let me say this, and I think we've talked about this before with vectors, that acceleration is defined as a change in velocity. So, if you're in your car driving, kind of my top-down view here, and you're going around a corner, well, your acceleration is going to be like this, but in your car, you feel like you're getting shot off to the side like this. And we call this the fictitious force, the centrifugal force. Centrifugal is the one that we say is fictitious. That's the one that points outwards. But actually, this is just Newton's law of motion, that a body in motion wants to remain in motion. So your body right here wants to continue along in a straight line. That's Newton's first law. But as your car turns underneath you, it feels like you're being thrown against the side of your car when actually the car is just turning underneath you. And you can do this at constant velocity. I'm sure all of you have taken a corner at constant velocity, say 55 miles per hour or something. We've all done that, made a corner at constant velocity. But to change the direction of velocity requires an acceleration. So try to remember that acceleration can mean a change in the speed, but acceleration can also mean a change in the vector direction while your speed is constant. And that's what happens with objects in orbit. Is an object in orbit has some velocity, and you have to have a velocity. Otherwise, it's going to be like me here. If you have no velocity, you're just going to fall straight to the earth and hit it. So you have to have a very specific velocity. And how specific? Well, just specific enough so the acceleration from gravity just changes your vector. And that's how you get your orbital motion around the planet, is that the acceleration due to gravity only changes the vector direction, but it's not actually changing your speed. And again, compare this to me just falling. If I just fall, well, my speed is increasing and I will fall and impact the planet. But an object in orbit, and again, you have to have a velocity. The velocity is the crucial part. You have to have this tangential velocity, we call it. It's going around. And then the acceleration changes the vector direction. It doesn't actually change your speed. And so this is what people mean. I think sometimes when they say that when you're in orbit, you're always falling towards Earth, even though you never hit it. And that's what they kind of mean by this. As you go around, you're always falling towards Earth. But what that falling is doing is changing your velocity vector. And so that falling towards Earth creates then this orbit around Earth. And again, you have to have a very specific velocity to do this. If it's any less, you'll fall into Earth. If it's any greater, you'll go away from Earth. So very specific velocity has to be done for that. And that's looks like what they're talking about here, because they're saying we see that the moon falls around the Earth. And that's what they mean here, how something falls around, that the acceleration is changing the direction of the velocity, but not actually changing the speed. And I'll say it for last time, the two things I think get mixed up is a person just falling towards the Earth versus something that has a velocity going around the Earth. In both cases, we say these things are falling, but I will hit the Earth because I have no velocity, while an object that has velocity can obtain an orbit then. So that's what they're discussing there, universal law of gravitation, and how things are always falling towards Earth and what they mean by that. Well, here's the official gravitational force, G, m1, m2 divided by r squared, again, commonly called the inverse square law, and that's just a math thing. It's not a physics thing. Totally mathematical, and why you'd call that the inverse square. And there's the value of G. Very small number, 10 to minus 11th, pretty small, just showing the weakness of gravity. And they're just giving some examples of, they're actually doing kind of a Cavan, well, this is a different method for weighing G. Just giving you an idea of an experiment you could do to measure the value of G. Again, capital G is something that has to be measured. We can't yet derive that in any way from physics. And there are other constants like that that can't be derived, that you just simply have to measure, which I know makes sense. We want the universe to tell us what the truth is, so let's measure it. And this looks more like just a standard type of plug and chug type of exercise that they're talking about here. And what I mean by that is, if we've got this piece of math right here, G being 6.67 times 10 to the minus 11th, so that's something you just might want to write down. that we'll need for maybe the homework to just do some calculating with this in our calculator here. And so plug and chug just means they're going to give you these values. They'll give you the mass of the sun, say, the mass of the earth. They'll give you the distance between them. And you just got to plug these numbers in and get your result. All right, so yeah, that was a weird edit there. I went off on a little tangent after that, and I wasn't happy with that. One of the things that's kind of cool about making videos, if I do go off on a tangent, I think maybe makes things more confusing, that I can just delete it and you never see it. So sometimes I do go into things more depth because, I really like physics, and sometimes I worry that may confuse things more than it needs to be. So I just cut that stuff out, and we'll go on to 9.3, gravity and distance, the inverse square law. And I was looking at this, and they're trying to give you some intuitive way of understanding it with paint spray and stuff. And again, if that works for you, then that's awesome. It doesn't work for me because I'm not a believer that physics is intuitive based, that I can just think hard and discover the rules of the universe. I'm just not a believer in that. So if this intuitive type approach works for you, I'm not at all. It just doesn't work for me. It doesn't work for me. But so that's kind of good. The book gives you that if that works for you. And I try to be more straightforward with the math and things and what's going on. Now I notice this picture here with the girl climbing the ladder, and what they're saying here is the girl's weight, not her mass, decreases as she increases her distance from Earth. So let me just say this again. The Earth, massive compared to us. Obviously, this is way out of proportion. But because the Earth is so large and its radius, the radius, the center of the Earth's like way down here, and we got this huge radius, that this little change right here in distance, where we live on the surface, doesn't really have much change in the gravitational field. Now, technically, because this distance is larger than this one, means technically the gravitational field is weaker here. It's weaker here than it is right here. But this difference is so small that we call this constant. And that's where our little g is. The little g, for us it's 10. Little g means the acceleration at the surface and something we treat as constant. And that's something that we can actually easily obtain with the force for gravity. Since the force of gravity is capital G m1 m2 over r squared, if this is the only force acting upon us, then we can use Newton's second law. Newton's second law says this equals ma, where the mass is one of these masses. And so these masses will cancel out, and we can get the acceleration at the Earth's surface, call that the sun, just by that equation there then, from Newton's gravitation, and also equaling Newton's second law. This A then is G. Once we put in, I put sun here. Once we put in the mass of the Earth and the radius of the Earth is how we get the value for G. It's at the surface of the Earth. So this is an approximation now. G equals 10 is an approximation, only at the Earth's surface. This is the real gravitational force. This is the real one. G equals 10 is the approximate one. And so what they're saying with the little girl here is the little girl has a constant mass. We all have a constant mass, assuming our diet doesn't change and stuff, but our mass is constant. What can change is our weight. Because remember, weight is another name basically for the force of gravity, m times g. And as this little girl climbs higher, now that we're using the official form for gravity, well, then her weight is going to be this. And as she gets farther away, then this distance increases, r. And as you divide by this number, your weight will get smaller. So that's what they're trying to say here, is the little girl, she's climbing up, her mass stays the same, but she will feel lighter. Because how you feel, that weight you carry around is from gravity. So as you go away from gravity, you will feel less heavy. even though your mass is still the same. And here they're showing what an inverse square law looks like. In other words, if you graph this mathematically, it looks like this, where this is your distance. And so as your distance gets closer, the gravitational increases. As you get farther away, it decreases, and it follows this. Well, this is called an inverse square function. That's what 1 over r squared would look like, something like that. And then these other constants here, like g, m1, and m2, what those do is they just affect the shape. Like, for instance, these constants can make it have like a sharper elbow, or maybe a more gradual type of elbow is what these constants do to that math function there. So weight and weightlessness, I was looking at this earlier. This one scares me a little bit. So we talked about weight and how a scale actually reads the normal force. A scale doesn't actually read your weight. And they give this example of being in an elevator. Again, an elevator, very common type of example because it's easy to understand because we've all experienced elevators. But when the elevator accelerates up, so that's the second case, you're going to feel heavier because not only are you feeling the force of gravity, but you're also feeling this acceleration pushing you up, and that just makes you feel heavier. And that's something we can do from Newton's laws to calculate that. And then when you go down, you feel less heavy because now the acceleration of the elevator is going down, and the value of g is also going down. And what they're showing now in this very right picture where they say 0 weight, they show the cables broken here. Well, in that case, the acceleration is now the same as that of g because we would say they're both in free fall. And so if the elevator is falling at the same rate you're falling, then you're going to lose contact with the surface. And what concerns me a little bit about this is they call this 0 weight. And that's what bothers me there because weight is mg. It's not like your mass went away, nor did g go away. You still have weight. What you don't have is a normal force anymore because you've lost contact with the surface. So if you can imagine that in your head, now this would be a scary scenario if the elevator broke, but if the elevator would fall and you fell with it, you would lose contact with the surface because everything is falling at the same rate. And so you would feel like you're kind of floating around in the elevator, of course, until everything crashed and you hit the bottom. But while things are falling at the same rate, you'll feel weightless, even though you technically will still have weight. That's mg. So that's what I don't like there, 0 weight. You have a feeling of weightlessness. Something that NASA does to train astronauts, and what is this thing called? It's called the Vomit. It's called the Vomit Comet. Something that NASA does to train astronauts. And what they do is they take a plane and they go way up high. And then they do a very sharp dive. And now this dive is very specific. They dive such that their acceleration is we use 10 for g. So the plane dives at an acceleration due to g so that the people in the plane feel weightless then, because now the plane and the people inside, so the plane and the people inside are all falling at the same rate. And so you lose contact with the surface of the plane. And so it feels like you're floating around. And that's because the plane and you are both falling at the acceleration due to gravity. And so it feels like you're weightless. But it's really an illusion, again, because your weight is mg. M doesn't go away, nor does g. You still have weight. It's just an illusion that you don't have weight because you can't touch a floor anymore. There's no normal force anymore. And so there's no scale to read your weight. And so you do feel weightless because you're floating around, but technically you'd still have weight. What you've lost is a normal force that you get when you contact the surface. And again, here's another picture that bothers me. this person in their car driving off a cliff with an exclamation mark. I guess that's something you should be worried about. They say both are weightless. I would definitely say it's not true, because the car has weight, so does the person. They both have weight, because weight, again, is mg. It's just that they're both in free fall, and so they've lost, there's no normal force anymore. They've lost contact with each other, and so they can't feel their weight, is something you could say. And same with the astronauts in the space station. They aren't technically weightless. They're in the case of the orbit again. Astronauts in a space station, they're not just falling, because if they were just falling, they'd hit the Earth. Astronauts in a space station have a velocity, and that velocity is what carries them around. They still have weight. But the space station and the person are both falling towards the Earth as it goes around. And so you lose contact with the surface. And I'm sure you've seen pictures of people in space. They're kind of floating around in a space station or something. That's what happens, because you've lost contact with the normal surface. But you aren't technically weightless. It's just that you can't experience your weight anymore because you can't maintain a normal force. So I'm being nitpicky there, I guess, maybe, but just don't like quite. I wish they would have said they're both in free fall and there's no normal force anymore. Ocean tides. So I was looking over this one, and this one I find a little scary because they really went hard on trying to explain the tides. And I will also give my best attempt here. And I think a lot of this is pretty complicated, maybe overcomplicated than it needs to be. And so if you want to check that out, you can. It's a pretty long section. All right, another cut, because I'm going to try that again. Again, tides. I was going to go with the way the book explained it, but actually I came up with a different idea. And let me try this. Let me, again, try to explain really quickly what the book is saying. And the book is saying this, that here's the Earth, here's the water around the Earth, and here's the moon. And because the force of gravity is dependent upon distance, r squared, the ocean here is a little bit closer than the center of the Earth. And so that means the force here is going to be a little bit stronger than the force at the center of the Earth, and it's going to be even stronger than the force on the other side of the water over here. And so I'm going to exaggerate this, but this creates a large force at the water, kind of a medium force, let's say at the center of mass of the Earth, and then a much smaller, well, not much smaller force, but let's just say a much smaller force at the other end of the Earth on the water there. And as you orbit, remember again, we're always falling when we're in an orbit, always falling towards our object. And so this part right here will create a bulge on the ocean. Now I'm exaggerating here, as a bulge. Just from gravity alone, we'll get that bulge there. And then what the book is saying is that then the Earth offsets a little bit. So we have this bulge, and then the Earth offsets a little bit because we have these different gravitational forces. And then this causes the bulge to be on the left and the right, which is what we have. There are 2 tides per day because there's 2 water bulges on the Earth. The one towards the moon tend to be larger than the one over here. And that's how they describe it. They describe it as having these different gravitational forces, and that pulls on the water stronger, then it pulls on the Earth, then it pulls on the other side. And so the water bulges, the Earth off-centers a little bit from the bulge, and then we're left with the other bulge on the other side there. That's what the book says, but maybe this might be a better explanation. And it just goes back to when I was talking about a car before. When you go around a corner, that when you're in your car, Newton's first law says you want to go in a straight line. And then when you turn your car, it feels like if you weren't holding on to anything, you'd slam into the side of your car like there was some force pushing you, but there isn't. It's just an illusion. Your body is continuing in a straight line while your car turns underneath you. And we could also say this with the earth, that when we have this water around the earth, and remember that it is turning, it's turning. And so this water here, according to Newton's law, wants to continue in its motion it already has, but the earth turns. And so this will create then the water to bulge out there where it's turning. And then we have the other bulge from the moon here. And that's another way that you could look at it. Again, if you look at explanations on YouTube, some people will call this the centrifugal force. And that's a little disappointing, because centrifugal is what we call the fictitious force. In other words, this force that pushes you out is what's commonly called the centrifugal force. And it's fictitious. It's an illusion. And it's another way that we could explain tides that's different than the book. And, the book goes really heavy into tides, and I just don't see that we need to go that heavy into tides. Tides isn't something we even explain in higher level physics at all. So, for instance, Physics 111, 121, 131, even in Physics 241, we still don't talk about the tides yet, because the math of this is actually a little bit challenging. It's not too bad, but definitely beyond what we should be doing in 101. But I guess I just wanted to give you a general idea of the tides and how the moon causes one side, but then the Earth rotating around causes the bulge on the other side. And that's what I think is you should really know about the tides. Overall, caused by the moon. The sun also does have some effect, not as strong as the moon, but sometimes they do align, and we get spring tides when they align. And I forgot what the other one is called when they are out of alignment, but there's another name for that. And just lastly here, this picture I'm looking at is they're saying a lot of stuff here that may look complicated, but what they're saying here is that when with gravity, that objects, when they're orbiting, they don't actually have a perfectly spherical shape, because as they orbit, it kind of causes the land to bulge out towards the center when they orbit. And same with the moon. It has little bulges on it. And these bulges create various torques. We're calling about the torque here. And after many, perhaps even millions of years, these objects will eventually come into a lock. And for instance, Mercury is in a lock with the sun. The moon is in lock with Earth. And what we mean by that is, after millions of years of this spinning around and these different torques happening, is that they want to end up having the same face towards each other. So try to imagine I'm on the Earth, and here's our point, and let's say here's the moon. Well, and here's my point on the moon as well. If the moon orbits but doesn't rotate, well, then the point will be here. And if the moon continues to rotate, our point will be here, and so forth until it originally gets back to our spot, and then we can see our point again from our view. But that's not what the moon does. The moon rotates, and it rotates in such a way, that the point of it is always facing the Earth. And so it rotates precisely so that one face of the moon is always looking towards the Earth. And this is usually called a tidal lock. I see they use that here. Interesting enough, this tidal lock is also working on Earth. So both objects actually want to come in a tidal lock. The smaller, lighter one will do it first. Earth, being much more massive, is going to take a longer time. But that's what tidal lock means. It means our moon specifically is orbiting so specifically that as it orbits, its one face is always facing the moon, the Earth. And this is why we say there's a dark side of the moon, because the dark side of the moon, we never see it. we never see the dark side of the moon because it never faces us. Because the moon's in a tidal lock, and so we only see one side. The only way we can see the dark side of the moon is to, get a satellite out there or some object beyond the orbit of the moon. And something I know that's true with Pluto. Pluto, very small, and it has a couple moons, but one of them, or maybe all of them, I know at least one of them, but one of them is such that they both orbit. They both orbit such that the same points are always facing each other. So in other words, not only does the moon orbit such that it's always showing the same face, but so is Pluto. So both of them are in tidal lock with each other, that this spins precisely as this one spins, so that they each face each other always. And that's a tidal lock of the planet and the moon, because they're both very small bodies. And I know Pluto's been demoted to a dwarf planet, and that's fine. Dwarf planets are something kind of new that's been discovered, and they realize Pluto fits more into a dwarf planet model than a planet. And so that's why it's been demoted, but it does have a perfect tidal lock, meaning that it orbits as well as its moon such that they both show the same face to each other all the time. And that's what you're calling about tidal lock here with the moon and the Earth. The moon is in lock with the Earth not yet in lock with the moon. And what do they say here? In a few billion years, our day will be as long as a month. And this is when the Earth will always show the same face to the moon. So that's when the Earth, so they're saying billions of years. I mean, I have no idea what that calculation is. So maybe, I know billion seems a long time. I'd go for maybe 10 million or 100 million, but I can't argue. I don't know what the actual calculation is there. But someday the Earth will rotate perfectly with the moon. Gravitational fields. So a field, what are they doing here? A field is technically a math object. Like they're drawing these arrows. We call this a vector field. A vector field means that every point in space has some vector to it. That's what a vector field means. That whatever point in space you have, there's some vector that's pointing. Now, in the case of gravity, that vector is always pointing towards the center. And that's what they mean by the Earth's gravitational field. It's a symmetric field. Every direction pointing the same. As you get farther away, it gets weaker. And because the gravitational field is symmetric is why we get spherical objects. Because a spherical object is the only object that will result when all the forces are equally pushing. So in other words, you can't get a square because the force of gravity is going to be stronger on these corners, forcing those corners to scrunch down into a circle then. And that's why we have objects as spheres. And now the rotating bodies is what causes the bulge at the equator. So getting the bulge of land at the equator actually comes from rotation. If there was no rotating of the Earth, though, it would have a very spherical shape to it. And what they're saying here is if you could fall through the center of the Earth, that the Earth's gravitational field actually gets weaker as you get towards the center. And the reason that is because there's less mass enclosed. So, here's the Earth. If you're standing on it, well, you feel the force of gravity from all this mass pulling you down. But once you're inside the Earth, now you only feel this mass pulling you down. And then once you get to the center, you're going to feel no mass at all pulling you down. Now you may be thinking, well, what about all this other mass? Well, if I'm at the center, then this mass over here is pulling me this way. This mass over here is pulling me this way. Everything is pulling me in equal directions. And so the mass that's around me is always canceling out. Now this is only true for spherical objects. But that's what they're trying to say here. As we get towards the center, the acceleration due to gravity becomes 0 as we get towards the center. And that's just because there's no more mass at the center to be pulling us down. And this is an interesting graph here. We actually just derived this a couple weeks ago in Physics 131 because we get the same result for the electric field. And what they're saying here is if you start at the center of the Earth, as you go out towards the surface, the gravitational field increases linearly while you're in the Earth. But once you get outside the Earth, meaning the surface, then you get the inverse square law. That's this decaying part here. But so a little bit of a difference here. I think this is actually a little bit advanced for 101, but here it is. When you're inside of mass, the gravitational field is linear. That's what they're trying to show here. When you're inside of the Earth, inside mass. But once you get to the surface is when we get then the inverse square law here. That's what that graph is showing. This I'm just not going to go into at all. This is where you have cavities inside of the Earth and what effects that have. And we talk about this also in 131 for charge. I don't see that we need to go there. And Einstein's theory of gravity. So interesting. They're going to bring up Einstein. So Einstein, vastly different understanding of gravity than Newton. And they give a common picture here of what Einstein's gravity is. So with Newton, we call this force an action at a distance. In other words, here's the Earth, here's the moon. There's nothing that connects them. This force of gravity is just some action that happens at a distance, even though there's nothing connecting them. Einstein's picture is completely different. And that's what they're showing here with this. They're trying to show like your bed. If you take a mattress and you lay in it, well, your mattress sinks down. And now if I rolled a ball in here, what the ball is going to do is it's going to go around in a circle. And there's some YouTube videos where you can find this, where people try to demonstrate in this three-dimensional way Einstein's gravity. Will take a sheet, and then they'll depress it in the middle, usually with a bowling ball or something, and they'll roll a tennis ball in here. And you'll find a tennis ball will go in orbit around the bowling ball here. Now, eventually it'll fall towards the bowling ball because of friction. But if there was no friction, your ball would come in here and just go in a circle around the object. And notice this circle is one of these circular lines here. And this is actually called a geodesic in math. And what Einstein says is that the shortest path is always a geodesic. And that can be a little bit maybe confusing to people because the shortest path you always think of as a straight line. But think of yourself on the Earth. If you're on the Earth, the shortest path is to curve. Now, you may be thinking to yourself, well, isn't the shortest path if I just bore through the Earth? Sure, yes. That is the shortest path if you bore through the Earth. But as far as we know, you can't bore through space-time. Now, that would be called a wormhole, which I know they're going to come up to in a little bit. But this is what Einstein means. The shortest path is a geodesic, this curved path. That's actually the shortest path. Because in Einstein's universe, you can't bore through space like this. You have to follow the path of space. And because space is curved, we get these geodesics, and those are the lines then. In Einstein's world, one could argue that gravity isn't even a force. That gravity is actually just the result of how objects move in a curved space. And so gravity with Einstein, vastly different than Newton. Does Einstein's theory of gravitation invalidate Newton's law? Absolutely. Absolutely 100%. They say no here. That's absolutely wrong. Absolutely invalidates Newton's theory of gravity. But here's what the deal is that think of the Earth again. The Earth we know is curved. Yet, you as a human being, when you look out, the Earth seems flat. And that's because on this curved surface, we're so tiny. We're just this little dot right here. And being this little dot, all we can see is kind of this flat stuff. We can't see the curvature. We're just too small. And this is what happens with Einstein's gravity, is Einstein says the universe is curved. But if we look at a very small portion of space like this, we can see it's flat. And in this flat area is where Newton's gravity will still work. But beyond this flat area, it's not going to work anymore. And there's other things that are even technically not true about this. So, for instance, if I have 3 masses, with Newton's gravity, I can just add this I can find this contribution for gravity. I can find this contribution for gravity. And then to get the total contribution for gravity, I could just add those together. In physics, we call that the linear, well, in math, actually, we call that the linear superposition, that the total sum of the forces is just summing the forces individually. That's something you can do vectorially with Newton's gravity, but not something you can do with Einstein. You just can't sum these individual pieces and get the total gravitational force with Einstein's general relativity. So what we say in physics is that, and it's actually quite fascinating from a mathematical point of view, because with Einstein's theory, if you reduce Einstein's theory to flat space, you get Newton's equations. So the math of Einstein actually reduces to Newtonian mechanics. And so while Einstein has invalidated pretty much everything Newton did, we still talk about Newton today because we live in this flat space. Because we're so tiny compared to the Earth and space, we experience this flat space. This tiny flat space is where Newton's gravity and Newton's laws all work very well, but they are technically an approximation to Einstein's overall theory. And let me just say this really quick, because we talked about this a couple weeks ago, that your final velocity is equal to acceleration times time plus your initial velocity. It's one of Newton's equations. Now this says that velocity can go infinite. If just given enough time, this number will go to infinity. That's what Newton says. Newton says you can go as fast as you want. But Einstein doesn't say that. Einstein actually says this is wrong. That you can't, that there is a finite speed limit, that being the speed limit of light. However, this does work when we're in this flat space. So that's what I see as the truth, that Newton has absolutely been replaced by Einstein, but Einstein's equations reduce to Newton's when we look at flat space. And that's why we still talk about Newton today, because the world we experience as human beings on Earth is mostly the Newton mechanics. The approximation from Newton is very, very close to what the actual answer is, the actual answer being from Einstein's general relativity. But once we get into more of curved space, then all of Newtonian mechanics will fall apart. Black holes. Wow, we're going to black holes. So black holes, the result of Einstein's general relativity. I'm pretty sure black holes were sci-fi ideas before Einstein, but Einstein was the one that really gave a physics credibility to black holes. So Einstein says that there isn't space. There isn't space. Einstein's saying there isn't time. There's no space. There's no time. What he says is there's space-time. And he uses this all as one word, space-time. And what Einstein argued is that these two can't be separated. Space is not distinct from time. You can't separate these. And so in Einstein's theory, they're combined into this one fabric that's called space-time. And I know you'll watch, well, I do at least, some videos sometimes, and they'll say, well, here's the space component and here's the time component. I mean, you can use those type of analogies, but technically it's not true. Einstein's universe is space-time. There is no space. There is no time. Only space-time. And this is a four-dimensional universe, and 4 dimensions impossible for you to imagine. And I'm not trying to rip on you. It's just that as human beings, we have no experience with the 4th dimension, and that makes it impossible to imagine. And trust me, I've tried. As a person interested in physics, I try all the time to imagine the 4th dimension. But try to imagine this: that in 2 dimensions, if you had 2 dimensions, and imagine a creature lived in this 2 dimensions. Now, in 2 dimensions, there's no top or bottom. So that means this creature only has skin on their sides. We can see their organs, because a 2-dimensional creature has no top, has no bottom. So as a 3-dimensional being, I can look at this 2-dimensional creature and not only see its outside skin, but I can also see its insides, its heart and beating organs, all at the same time. All at the same time. And this is what's true with 4 dimensions. 4 dimensions means that if you look at a person, you can see their skin and all of their organs at the same time. And that's impossible to imagine. You can try, but trying to imagine the 4th dimension, to me, that just seems impossible. It's so beyond our experience. So I was going with black holes. So mass creates, I'm trying to draw 3-dimensional here. Hope it doesn't turn out too bad. But I'm trying to create a depression here, that our sun creates a depression, and then Earth orbits around this geodesic, this line that goes around it. A black hole is when you get a rip then, where this depression becomes so deep that it's seemingly just, well, we're not sure what happens because all the math breaks down, but not sure what happens at the very center of a black hole. In other words, does it rip space-time? Is this just a very, very deep hole? Still not quite known today, but that's what a black hole is. It's this big hole in the fabric of space-time. And this hole gets so, well, here's a good picture. Here's a good picture of what I'm trying to draw right here. And this gravity can be so strong that not even light can escape it. So light will just get sucked into it too. And that's why we call it a black hole, because nothing can escape it, not even light. And here's the first picture of a black hole. The black hole always being the black circle. Now there is light around it, because what happens with a black hole is it's got a gravitational field, and so all this matter will come into the black hole, and it forms what we call an accretion disk around it. And all this matter here is colliding and heating up and giving off light. And that's what you see in this picture here. This is the accretion disk that's around the black hole. This is where all the matter is coming in and colliding with each other before it gets sucked into the black hole. And it creates all this light and other phenomena that happens too. A wormhole. Wow, they're really going sci-fi here. All right. Well, a wormhole is another idea that actually can be found in Einstein's equations. Einstein equations allow for a black hole. Now, a black hole is something we've already seen in the universe, but Einstein's equation also can yield what he called a white hole. So there's a black hole and there's a white hole. The black hole sucks everything in. That's what we know for certain exists. The white hole is something that spits everything out then, which is something we haven't seen yet in the universe. But Einstein's equations do allow that. And this is what's commonly called a wormhole, meaning that if you go into the black hole, you'll get spit out some other end. Now, where you get spit out, no one knows because we don't even know if this is true. Just because the math says it's a possibility doesn't necessarily mean it's true, although Einstein's equations have yet to be shown false. So, well, time will tell. Time will tell. Hasn't been seen yet, but I gotta say this one bothers me a little bit too. Stephen Hawking, a pioneer expert in black holes, I wouldn't agree with that. Was one of the first to speculate about it, but that's definitely not true. It's well, that's amazingly not true. And I'm just going to pull out my keyboard here really fast, but I have no doubt that, I don't know if you guys can see this, but if I type in Einstein-Rosen bridge, I bet I'll get wormhole. And there it is, wormhole, Einstein-Rosen bridge. The wormhole is was speculated way before Stephen Hawking. So, like I understand, the guy's passed away. He made his contributions. His contribution is pretty technical. It has to do with quantum mechanics, but he argued that with quantum mechanics that you could have a particle that falls into the wormhole and then loses information while this other particle could escape. It's called Hawking radiation. Hawking radiation. And that was his contribution to black holes. Definitely a good contribution. I don't want to rip on the guy, but he was not the first to speculate wormholes. That's definitely not true. Universal gravitation. And I don't know what more there is to say. I know there was one thing more I wanted to say, and I forgot. I missed that scrolling through. I'm just going to scroll really fast. This is a very technical, minor thing. Remember, I'm a physics math guy, so I kind of like things to be somewhat appropriate here. And, man, I don't know if it's really worth going through this, but I thought it might be a point of confusion, and I just wanted to say something. And where was that? Oh, here it was. This was just something I noticed that I thought was a little unfortunate. Because they're using this tilde sign here. They're using this tilde sign. They're saying F tilde A. Now, the tilde in math is most commonly used to meant an approximation, that we're approximating something, is why the tilde is commonly used. But they're trying to use this as meaning proportional. Proportional actually uses this alpha symbol. This is the proportionality symbol in math. That's what means proportion. And it's just something I want to throw out there, because right here when they say check your answers, they say F is approximate to A is a proportion. And look, that's true. F equals MA. That is a proportion. I'll tell you what a proportion means in a second. But the math for that should technically use the alpha symbol. The squiggly tilde means approximate. So in other words, the approximate force of gravity is mg. That's where we would use the approximate there for mg. Proportion means, so because they ask a little bit about proportion. Proportion simply means that you have something related to something else simply by some constant. That's what proportion means. So if I have force and I have acceleration, these are proportional if there's only a constant that's different between them. Another thing that we could say is proportional is like displacement is proportional to time when there's no acceleration, because that proportionality is v, the velocity. So proportion means that these two variables are simply related by multiplying by a constant, is what proportion means. And that's just what I wanted to say about that mass symbol. Let's check out the homework. All right, so number 1. What happens to the force of attraction between two planets if their masses are doubled? All right, let's just stick with the first part there. So force of gravity, G, mass 1, mass 2 over r squared. So the first thing you're saying, if the two planets, if their masses are doubled. So let's do that first. Doubling the mass means we'll have 2 mass 1 and 2 mass 2 because we're doubling them, so we're multiplying these masses by 2. And then what are they saying about the distance? The distance between them is also doubled. All right, so instead of r, we're going to double that, which means 2r. But remember, this is ultimately squared, that distance. So if we just look at this, 2 times 2 is 4. So in the numerator, we'll get a 4. And 2 squared is also 4. And then r squared is r. And so we can see these 4s will actually cancel. And then we're back to the original force of gravity, Gmm over r squared. So under these conditions they've given us, the force would remain the same. The constant G in Newton's equation produces equilibrium, was measured by Newton, makes the units of measurements consistent, shows gravity be a relatively huge force. Well, I didn't say this, but it was measured by Newton. G doesn't produce equilibrium. G makes the units of measurement consistent. That's weird. G does help make the units of the equation consistent, but not units of measurement. I'm not even sure what they mean by that. And shows gravity to be a relatively huge force. It's not. G is actually very small. Shows that gravity is actually a relatively small force. I'm wrong about that? Wait, I should try again. Well, I'm going to have to go with the one that makes no sense to me then. This one that makes no sense to me is the one you want. I need to pause for a second and think about that. All right, well, after some research, it looks like Newton didn't ever measure G. But to try to make sense of this one, I'm going to go with what I originally said, is that force is in units of newtons. And if we look at mass 1, mass 2 over r squared, well, mass times mass is units of kilograms times kilograms. And then r is in meters, and that's squared. So we get meters squared. Now, Newton, the unit Newton is ma, m being mass, and acceleration being meters per second squared. So if we have m1, m2 over r squared, and this has to have units of newtons, well, it doesn't. It has units of kilograms squared, has units of kilograms squared over meter squared. But we want this to equal kilograms meters per second squared. And so in order to get these to equal, we have to multiply by something to do that. And so this is kilograms squared, but this is only kilograms. So we have to cancel out one of these. Here we have meters squared in the denominator, but we want 1 meter in the numerator, which means the numerator would have to be meters cubed. So cubed divided by squared gets us a meters in the numerator. And then finally, we need a second squared in the denominator. And so we have to have this unit in order for this expression to come out as newtons. And this is what I think they're meaning by the statement. It's the word measurement that I don't think is the right word to use. I would say this balances the equation. that it makes the result come out as newtons, and that's one of the functions that G does serve, is to make this result have units then of newtons. So I'm going to go that's what they were going for there. I just think the wording is unusual. Measurement doesn't need to be here at all. Again, I would say this is to make sure the equation is balanced, that both sides have the same units is what they're going for there. And let me just say, hey, if a question confuses me, then I don't think that's a good question. So that's not something I'd put on a test. I only pick questions that I think are good questions. Again, this is the practice part. So after having done that last one, don't consider that a good question. When you weigh yourself on a bathroom scale in an elevator accelerating upward, are the springs in the scale more or less compressed accelerating downward? Wait, what? There's two questions here? Oh, there are two questions, and so we got to answer both of these at the same time. All right, I wish they wouldn't do that. I like one question at a time personally for tests and stuff. So if an elevator's going up, then this force is pushing on you, the elevator going up. This makes you way greater. I'll use a greater than sign there. So if you're accelerating up, that makes you feel weight greater. If you're accelerating down, that makes your weight feel less. And as a matter of fact, if you accelerate down at the same rate as the acceleration due to gravity, then you're going to feel like your weight is zero. That's what you're going to feel like, even though your weight is still technically mg. Remember, weightlessness is more of an illusion because you lose contact with surfaces, but you aren't technically weightless. So I'm going to say your weight goes up and it goes down. So, I'm looking for compression of the spring. All right. Going up means it's compressed more. So compressed more going up because the spring is squishing. But as you go down, the spring will be able to expand a little bit more because you're feeling less. So I'm going to go with a more and a less. So here's a more and a less. Here's a less more. Here's a less while and a more while. So the only one here is, what did I say again? More or less. That's the first one. And why are occupants of the International Space Station weightless? All right. Well, if a physics person asked me this question, I'd say, well, they aren't weightless. Their weight is the force of gravity. So again, weightlessness is something that is more of an illusion. You still have weight. Again, and now the reason, let me just say this again, I tried to talk about this earlier, but it has to do with acceleration also changes the direction of your velocity. So you can have an acceleration while your speed remains constant. And that's how we end up getting these orbits around the Earth, is that the object's always falling towards the Earth, but it's always moving in either to the right or the left. And so we say it's constantly falling to the Earth, but it never reaches it because it's in this orbit. And so that's what I'm going to look for. They are in free fall, looks like the best answer. They are so far from Earth, I'm just going to ignore that. Centripetal force is fake. The floor of the space station is made from what? Some fake material, I guess. I don't know. Nothing blocks gravity. As far as we know, nothing blocks gravity. So the only one that makes sense to me here is the last one. And that's what we mean by an orbit, is they're always falling. It's like free fall, except you're moving to the right or to the left. Why is it not possible to directly observe or photograph a black hole? Well, Look, that seems like a strange question to me because we just saw a picture of a black hole in the text. So, I mean, I get what they're going for. They want us to answer with that light can't escape a black hole. I get what they're saying. That if you just have a black hole, light can't escape it. I get it. But look, the black hole has a giant accretion disk around it, and that makes tons of light. That's how we see a black hole. We see a black hole because of its accretion disk that's around it. Now, I don't know with 100% certainty if this is true or not. I'm willing to go on a limb and say it is, though, that all black holes have an accretion disk. That there is no black hole. Now, I could be wrong. I am going out on a little of a limb here because I really don't have this data. But black holes are always sucking things in. It seems to me that all black holes will have an accretion disk of some type, that it's going to be extraordinarily rare to find a black hole just by itself. So, if we have the blackness of space, so I'm drawing stars here, if the black hole was only by itself, then you wouldn't see it. You would notice it maybe by not seeing stars there. But I think the truth is all black holes have an accretion disk. That's how we can see them. I don't think black holes just exist as a black hole alone. There's other elements to the black hole that allow us to identify it, which again, you saw with the picture in the textbook. So, now again, I know what they mean. They mean this answer here. The gravity is so strong that not even light can escape the black hole. That's what I know they're getting at. But on a bigger picture, I don't like, I guess, that they think the black hole just exists by itself. There's other components to the black hole which allow us to find it. Again, you already saw that picture in the textbook. And check out, well, like I just got to see, I saw another black hole. I'm interested now. Why is black hole what? Is this not? This is basically the same question. Why is a black hole invisible? Well, they're going for the same thing, that light can't escape it. That's really literally the same question as the other one. All right. I noticed they say dwarf star here, and I didn't say anything about that, but the cycle of stars, let me just say this really fast. How a star dies depends upon how massive it is. So, for instance, our sun, pretty typical size sun, and it's not massive enough to form a black hole. Now, when a sun dies, that means it can no longer produce its nuclear fusion, because that's what happens in the sun. Particles are fusing together in a nuclear process, and that gives it its light. But eventually, all that fuel will burn out. And when that fuel burns out, you'll be left with a dead star. And now our sun will become what we would call a white dwarf. And a white dwarf is basically the core that's left over of our sun. A very compact, very small, pretty heavy. But that's what a typical star will go into. As the mass gets larger, as the mass of your star gets larger, it could die differently. So if the mass is large enough, what's happening here is that the gravitational field is trying to collapse the sun. But because the sun is so large, it's pumping out all this radiation. It's kind of pushing back. It's pushing back against the gravitational forces trying to crush it. But once the sun loses its fuel, the gravitational force wins, and it'll collapse the sun. And if the mass is large enough, then it'll collapse into a black hole. But you have to have a very large sun for that to happen. So most run-of-the-mill stars will collapse into a white dwarf. They say black dwarf. I'm not even sure what a black dwarf is, actually. But there is a death cycle to suns, and how they die does depend on how massive they are. Your average typical star will just will just come into a white dwarf like this, while the very extremely heavy stars, once they lose their nuclear fuel, gravity wins and it just crushes it all into the black hole then. And lastly, it's just a chug and plug problem. So I actually don't have my calculator here with at the moment, but let me just say this. They just want us to calculate the force of gravity. So in my calculator, I would do, well, let me write the actual formula, m1 m2 over r squared. So I would do g 6.67 times 10 to the minus 11th. This is what I'm punching in my calculator. And then times mass 1 is the Earth. So that's 6 times 10 to the 24th. The other mass is the moon. So I'd multiply this then by 7.4 times 10 to the 22nd. And so that's G, M1, M2, all divided by, and then the distance they're giving us is 3.8 times 10 to the 8th, and then that needs to be squared. And so that's what I'd punch into my calculator and get the result they want. So there is our homework. They even call this plug and chug, because that is a common name for doing this stuff. You're just plugging in numbers and chugging the answer out with your calculator. So, well, there is chapter 9 homework. I will talk to you in the next video.